Hey folks, today we're going to be taking a look at aldehydes and ketones on the MCAT. And if you look at a textbook, you'll see there's considerably less information on the MCAT than in your textbook, which is probably a good thing. And this is true for most areas of orgo. First of all, we're going to describe aldehydes and ketones. So they both have something called a carbonyl group. And a carbonyl group is going to have C double bond O like this. And the carbon is going to be considerably positive compared to the oxygen. For this is going to be because of resonance. What will happen is the oxygen is not only more electronegative, but it also has a pi bond here, which allows those electrons to be kicked up into the oxygen. And this will describe its reactions. And I can't speak today. Okay, so over here is what it looks like. So molecules that are going to have a carbonyl that we're going to be looking at will either have a hydrogen here, or they're going to have two alkyl groups or R groups like this. And if they have a hydrogen here, then they're going to be an aldehyde. And if they have two R groups, they're going to be a ketone. Now, in the case of the aldehyde, the simplest aldehyde would look like this. It would have two hydrogens on there. And the next simplest would look like this. We'll put a methyl here. So those are the first two aldehydes in terms of numbers of carbons. As far as ketones go, the very first ketone is going to look like this. It's going to have two methyl groups on each side of the carbonyl, which is here in the center, in order to be a ketone. Now, there are two forms of naming, the common and the IUPAC. And in the common area, there's actually more than one common method. Fortunately, it's really, really easy. Now, what happens is in we use stuff like meth and eth to indicate the number of carbons. This would be one carbon, this would be two carbons like this. So we will be talking here about the IUPAC system, the International Union of Pure and Applied Chemists. But in the common system, which was developed first, what happens is when we have one carbon, that's going to be form. And when we have two carbons, that's going to be a seat. And you don't need to go any further than that with the common naming. So if we name this molecule right over here, as far as the common IUPAC system, it's going to be one carbon and it's going to end in al. So what we're going to have is, this is going to be methanal. That means a one carbon aldehyde. And that al is the IUPAC system way of telling you it's an aldehyde. Now, as far as this character goes, that would be ethanol. And if you go into the lab, no one will ever call this methanol and ethanol because the common names are so entrenched. So what happens is, if we look at the common system, we get here form, but we don't say formal, we say formaldehyde. So formaldehyde is the common system. And then for ethanol, we're going to call this acetaldehyde. So that's the basic system. Now, what happens is, if you have a long chain like this, a semi-long chain. And let's say that this will be an aldehyde here. And let's say that here we're going to put an OH, and we want to name this. So what happens is we're going to number it from the end with the aldehyde. Now, the reason we're going to do that has to do with priorities. These are naming priorities, and this applies not only to aldehydes and ketones, but to everything. Yeah, I know I didn't spell that right, but I'm not good at that. So what happens is the lowest priority is going to be an alkyl group or a halide. And then after that, an alkene and an alkyne. And after that, a OH group, and not as important, but an amino group. And then after that, a carbonyl group. And then after that, a carboxylic acid or any of its derivatives, like esters and like acid chlorides and stuff. So we'll say derivatives. So what happens is that almost everything is a lower priority. Almost everything is going to be a lower priority. So when we're looking at that, the OH is to the left of the carbonyl, so it's a lower priority. Therefore, the parent name will be taken on by the aldehyde or the ketone. So we have 1, 2, 3, 4, 5, 6. So this is going to be called hexanal. Hexanal. And then we're going to number it from here. And then this would be 5-hydroxy. So the point is, anything of a lower priority will not take the parent name. So alcohols are typically called ol. Alcohols are called ol. We won't call this ol. We're going to call it hydroxy because the ol is a lower priority. So what happens, though, when we get over to here? So let's go ahead, and we're going to take this now, and we're going to put a carboxylic acid on here like this. So we'll grab that here, stick that on there, and there we go. Okay. So what we've got now is we've got an aldehyde, and now I'm going to replace that with an OH right over here. So there is the carboxylic acid. And then I'll take that OH and I'll turn it into a carbonyl. Now, it doesn't matter if this is an aldehyde or if it's ketone. It doesn't matter. Because if it's carbonyl, it's going to have a lower priority. And if it has a lower priority, its name is going to be like the alcohol, something different than what we're used to. And that name is going to be oxo. So the name for this is going to be 5-oxo. And then we got 6 over here. So then this is going to be hexanoic acid. So the acid having a higher priority will take the parent name, the name on the end, and the ketone in this case will be called oxo. So that's the idea behind that. Now, there's a couple weird things that happen in the naming. For instance, if you go ahead and you take this molecule over here, okay, clearly when we're dealing with the IUPAC, and I think I was using red for that, yeah. So this is going to be called propanone, because one means aldehyde, it means ketone. Okay, so it's propanone. And there's no reason to call it 2-propanone because it can't be anything else. Because if it's a ketone, the carbonyl must be on the number 2 carbon. So it's traditional not to use the numbers unless you need to use the numbers. In fact, it's actually wrong, but teachers often allow that on tests because they're trying to encourage you to be a good human being. Okay, but what happens if we're going to call this with a common name? Really weird common name. They call this acetone. Now, we know this means 2 carbons. So where did they get the acetone? Well, it turns out that this part is 2 carbons. And what they're doing is they're saying it's a ketone. And we're going to assume we need to add 1 more carbon. We're going to assume that in the name, which is kind of dumb. And when we assume that, it's going to be acetone, meaning it's 2 carbons plus 1 more. So it's not a very systematic way of doing it, really, but that's the idea. And what you can do with this is you can do something like this as well, CH3, C double bond O, and here this is a phenyl group. So what we have here is, this is a phenyl group, and then this is a methyl group. And there's several ways to go about naming this. I mean, we could go about naming it the IUPAC way. And if we did this, it would be 1 phenyl, and then it would be ethanone. So we're starting numbering over here. And then there's a phenyl on the number 1, and it's a ketone. Now, I don't know if that form will be on the MCAT. It's a little fancy, but that's how the IUPAC would look. But then if we're going to name this by the common name, we would look at this and would say, okay, this is 2 carbons. This is acete. And this is going to be acetophenone. Now, the O is there to make it sound good. The acete is 2 carbons, and then we have to add a carbon. But if we didn't say it, we would say like acetone. We didn't say that. We said phenone. That means that there's not a methyl there, there's a phenyl there. Okay, also, this is a dumb way to do it, but this is how they do it. So they say, well, it's a ketone, it's aceto, and since we brought this up, what's connected is a phenyl. And really, this is what everybody calls it, acetophenone. But then there's one other system that I really like because it's so easy. What you do is you alphabetize these 2 groups on the carbonyl. So this group right over here is P, this is M. M comes first. And then you call this methyl phenyl ketone. So this is another system where you just take the R groups and you name them alphabetically, and then you put the word ketone there. And this is very nice. Anyway, that's the nomenclature of aldehydes and ketones. Now what we're going to take a look at is how they appear when you have them typographically. Typographically, aldehydes are CHO, and you can work that out. And typographically, ketones are going to be RCOC, where this represents the carbonyl. And some of the naming is definitely not on the MCAT. I think what we've covered is pretty good. Okay. And now what we're going to take a look at is we're going to take a look at the physical properties. Now, here's the idea behind this. These are all approximately the same molecular weight. They all have 4 carbons, they have, including oxygen and carbon, they have 4 large atoms. And so they're all going to be about 60 is their molecular mass. And we're going to be looking at their boiling point. Now, butane has no oxygen or nitrogen or fluorine. It's completely carbon and hydrogen. It's a hydrocarbon. So what that means is it's going to have really not a lot of intermolecular forces, just London dispersion forces. That means it's going to boil at a very low point. And propanol, because it has hydrogen bonding, that has hydrogen on oxygen, nitrogen, and rarely on fluorine, because that would just be HF. That's going to have a lot of intermolecular forces, hydrogen bonding. And so that will have the highest boiling point. And as far as the aldehydes and ketones, those will be polar non-protic, those would be in the middle. As far as solubility goes, basically it just has to do with the number of carbons like everything else. And I don't think you're responsible for the exact number, but what we see here is when you have like about 5 or 6, it's going to be soluble or very soluble. And when you get to 7, it becomes insoluble, just a real nice cutoff, just roughly around there. So what happens is all of these are going to be aldehydes or ketones. And then when you start getting to a larger number of carbons, you don't need to memorize the number, just the concept. You're going to have insolubility. So that takes care of that pretty nicely. Okay. As far as important reactions, the first one we're going to be looking at is nucleophilic addition reactions. Oh, that's all of them. So what happens is that you have a carbonyl group like this, and a nucleophile is going to attack, and something with a lone pair or with a partial negative charge. And what will happen is when it attacks, it's going to attack the carbon because the carbon will be partially positive charge as a result of resonance, and it will come in like this. And that's what all of these reactions are going to be about. So the first thing we're going to look at is acetals and hemiacetals. So what happens is if we start with something like this, so there we have an aldehyde. We can react this with one alcohol and H+. And what's going to happen is we're going to end up with something that looks like this. And I'll show you the mechanism in a minute. And then if we use a second equivalent of the alcohol and H+, which is the catalyst, then what's going to happen is we're going to get an OR here and an OR here. And that's how it will look. Now, as often happens in organic chemistry, they change the way the naming system works. So originally, this was called exclusively the hemiacetal. And it was done so for 2 reasons. It was derived from an aldehyde, and that's where the ace comes from. And it's halfway to the final product, and that's where the hemi means halfway. So this was the hemiacetal, and then this over here is the acetal. Now, if we went ahead and did the same thing here with a ketone, then what would happen is we would get an OH and an OR, and we would get an OR and an OR. And originally, this was called a hemiketal because it was derived from a ketone. And this over here was going to be a ketal like that. And let me see if I can fix that. Good. So this would be our ketal. So they thought it important to differentiate between the starting material of the aldehyde over here and the ketone over here. But then a problem arose when they were working with large molecules and they were using aldehydes and ketones. Being specific about whether it was a ketal or an acetal became a pain in the butt. And so more recently, they have dumped this. They're still using it because that's what always happens. But what happens, they dump this and they said, look, let's get rid of the ketal and the hemiketal. What we'll do is we'll just call this a hemiacetal. And we'll call this an acetal. And then I know what you're saying, but they were derived from ketones. Yep. But if you look at all the modern books, you'll find out that there's very few ketals and a lot of acetals. So let me explain. The older system, which is still in use and could be on the MCAT, is that aldehyde-derived products are hemiacetal and acetal, and ketone products are hemiketal and ketal. But in the modern parlance, they only have hemiacetal and acetal. So that's the way that works. Now, what happens is if we go ahead and we take a carbonyl like this and we add an H plus here and an alcohol like this, what happens is this is going to be protonated, and then that's going to give us a positive charge here. And then the alcohol that we have here is going to come along and attack like this. And then when this alcohol comes in and attacks, this will become an OH right over here, and this will become an OR and an H, and then this will have a positive here. And then what we do is we have some kind of a base come along, and that base, it doesn't matter what it is, grabs that proton. And when that base grabs that proton, this positive is going to be neutralized. And so what we get over here is we get an OH here, and then we get an OR, and this is our hemiacetal. So that's halfway to there. Now, do I think in the modern MCAT you really need all of this? You probably want to have it because it's listed on their important reactions, but you probably do not need it in this precision. Probably, but there's not a guarantee. So the way to study is study the most likely things first and then go into things like this, which I think are not as likely because the MCAT does not stress mechanisms to this degree as much as they used to. Anyway, what happens next is we're going to have a proton like this and a second equivalent of the alcohol. And then what will happen is we'll have this protonation creating water as a leaving group. So we get this water like this and the positive here. And then we have our OR like this. And what will happen is these electrons here are going to drop down and then the water is going to leave. So what we'll get will be this, an oxygen with a lone pair, and then our R group with a positive charge right there. And what happens next is we're going to have our alcohol attack. So here comes our alcohol, it's lone pair, and then this is going to drop down like this. So what we get is here an OR, and now it's neutral, and then we have an OR and a hydrogen here, and then our base comes along, this is positive. Our base comes along like this and grabs this hydrogen like so. That drops down, and lo and behold, we now have our acetal like that. So it's a little fancy, but it follows the way a lot of these reactions work when we're dealing with aldehydes and ketones. So the question is, what good is all of this? And what it's really good for is going to be, you're going to adjust that? Okay. What it's really good for is creating protecting groups. And what happens is you could create a protecting group. Let's say you had something like this, double bond over here. You have an ester like this. And then you could say, okay, I'm going to add 2 alcohols. Okay, we got 2 alcohols, we got H plus. And then what's going to happen here is you're going to get an OR and an OR. That's your acetal. And then over here, you'll have your ester. You could do it that way, but it's usually not done that way because they've got a better idea. In order to get a really good reaction, if we can get these 2 alcohols here really close together where they can't get apart, then we're going to have a better reaction because we'll have a better equilibrium constant, more favorable. So what they do instead is they do something like this. All the leaving groups look like this. We've got our carbonyl here, and then what we do is we use this stuff. This is ethylene glycol. Ethylene glycol is antifreeze. And when we do this with H+, it's got the two alcohols here. So what's going to end up happening is we're going to end up with this, and then this is OR, and then here what you get is you get your O, and then these two carbons right here are going to be right over there. So this would be a cyclic acetal. Cyclic acetal. Okay. Now, this cyclic acetal is considered to be a protecting group. And the way it works is this whole reaction we've been doing is acid catalyzed. It's acid catalyzed. So if we stick it in base, this is locked in place. And for a protecting group, that's what you want. You want to do a basic reaction. So if we take this and we go ahead and react this with something like lithium aluminum hydride, that is a very basic reaction. And it turns out, as you see, the acetal does not form on the ester. It doesn't form on the ester. It forms on the aldehyde or ketone. So we can differentiate between the two. We can protect the aldehyde or the ketone from reaction by the lithium aluminum hydride, which is basic. And we can do something to the ester. And what we're going to do to it is reduce it, because this is a reducing agent. And this will be protected from the reduction. So what will happen is this will turn into this. And as far as the protecting group, it will remain just as it is. And then all we need to do is take this and react it with H3O+. And when we do this, this will get protonated and this will get cut. When you cut this, you cut it next to the oxygens, and then you add a double bond O right over there. That's how you do it. So what we end up getting looks like this. You get your OH here, your H and your H, and then this becomes your carbonyl group. Now, what would have happened if we didn't do this? If we didn't do this, the lithium aluminum hydride, a reducing agent, would have reduced the carbonyl to the alcohol. And if we don't want that, we need to protect it. So that's the big deal behind cyclic acetals. Okay, it's not that all they're good for, but it's most of what they're good for. Okay, let's take a look now at another exciting reaction involving imines and enamines. So what happens is if we take a ketone like this, and we react it with something like this. Now I'm using cyclic here because it's fancy and I like it. But what we have over here is, oh, I don't want to do that. What I want to do is this, because that would be uglier. Yeah, we'll just do it like this. That's perfect. Okay, so here we have an aldehyde or a ketone. And then on the right, what we have is a primary amine. Now, the way it works is a primary amine is going to have two hydrogens here. And the reason it's going to be primary is it's got one R group there. One R group is going to make that a primary amine. And what we're going to do is we're going to have this react with a pH of about 4.5. That's not that important. And what we can do is we can use something called lasso chemistry. So the way lasso chemistry works is we're going to grab these hydrogens over here, and we're going to grab this oxygen. Now, my teacher was a great teacher. He used lasso chemistry, but they came down with an edict saying that you should never use lasso chemistry because people will not learn the mechanisms. However, for the MCAT, that may not be a bad thing because a lot of times you don't really need them. What you need is you need to understand that you're going to get something that looks like this. And you also need to understand what this is called. This is called an imine. And the structure of an imine is C double bond N, like that. So that's what we're going to end up getting for that. Okay. Let's see if I can find what I'm looking for. Yeah, that's what I'm looking for. Okay. Now, biologically, there's a lot of interesting things that happen with imines. The A1C test for blood sugar is actually a test of the number of amines you accumulate in your hemoglobin. We're not going to go into that, but it's a reaction of sugar, which is a aldehyde, like sucrose, and the amines, it's the terminal amine on the hemoglobin chain. Okay, you probably don't care, but I told you anyway. So let's go ahead and take a look at another case over here. What we're going to do is we're going to come over here and we'll use an aldehyde or a ketone. This is a ketone. And then what we'll do is we'll put a nitrogen here with a single hydrogen. And then we'll do all this. This is what I was doing last time. So this is a secondary amine. So we found that we got an imine with a primary amine. Let's see what happens when we use a secondary amine. So the lasso chemistry is slightly different. What we do is we're going to put these together, the same pH, and we're going to grab this like this. Notice where the bonds are. This drops down like that. And that will give us a structure like this. And this is an ene. And this is an amine. So we call this an enanine. And it turns out that synthetically, there's a rather a large number of cool reactions we can do with these, but they're not on the MCAT, at least according to the people that make the MCAT. So you just need to know how to get to there. So I guess what I want to do is just emphasize that it's all about whether you have a primary amine or whether you have a secondary amine, whether you get an imine or an enamine. And that's what they're doing over here. As far as the mechanism, it's almost identical to what we just did. What happens, though, is rather than a proton attacking, it's going to be the nucleophilic nitrogen that attacks, and these electrons swing out to the oxygen like so. In the next step, we have protonation right over here, and then we have an additional protonation right over here. So what's happened is we now have water, which is our leaving group. And then this lone pair here drops down. That's going to form the amine. And then we remove this hydrogen. And when we remove this hydrogen, it neutralizes the nitrogen. And that gives us the imine. Okay, I went a little fast, but you can look at it. Makes sense of it. I don't think you're going to need it. You might need something like what's the nucleophile, and is there a dehydration or something like protonation involved. But what's interesting is the enamine reaction is really almost identical to this, except in the last step. In the enamine reaction with a secondary amine, this hydrogen over here is an R group. So you can't remove this. So you can't get an imine. But there's a hydrogen here, and that hydrogen is removed. And when that hydrogen is removed, the electrons swing down to here. That's this reaction right there. So these electrons swing down, and these electrons swing on to the nitrogen, neutralizing it, and you get your imine. So that's the reason why there is differentiation between imine and enamine. It's in the structure of the amine, whether there's a 2 carbons present, enamine, 1 carbon present on the carbonyl. Okay, so let's see what I'm supposed to do next. Okay, yeah, here we go. All right. I want to say, isn't this fun? But I won't. Okay, so here's the deal. A lot of chemicals have been written in such a way that they have hydrogen on the right-hand side. Lithium aluminum hydride, sodium borohydride. Those are these chemicals. But they're not just these chemicals. They're also NADH and NADPH and FADH2. Now, all of these have hydrogen with a negative charge. These are highly reduced molecules, so they're reducing agents, okay, because they will be oxidized when they react with things. This is going to be strong. And this is going to be weak. Basically, aluminum is a metal, so it'll have a positive charge to make these hydrogens more negative. Boron is not a metal, so it won't make these hydrogens as negative. This is a strong reducing agent. This is a weak reducing agent. Now, what happens is, if you are a weak reducing agent, you basically can only reduce a very limited quantity of things. And those things would be aldehydes, ketones, and the strongest reacting carboxylic acid derivative, acid chlorides. So sodium borohydride does not react except with aldehydes, ketones, and these guys here, okay, acid chlorides. Lithium aluminum hydride is going to react with all of these. Plus, it's also going to react with carboxylic acids, plus the derivatives, which is a lot. So that's why you want to use one or the other. You want to use one or the other because you want to know what you're going to get. And this will allow you to make a choice based on the strength of the reducing agent. So what do these guys do? Well, let's say that over here you had a carbonyl like this, and then let's say over here you had a carboxylic acid. If you took this and reacted it with NABH4, NHBH4 does not react with carboxylic acids. So because of that, it will simply reduce the carbonyl here to the OH. And when it reduces it, the carboxylic acid is going to remain in place because it doesn't react. On the other hand, if we take the same molecule and react it with lithium aluminum hydride, now what's going to happen is it's not only going to reduce the ketone, it's also going to come over here and reduce the alcohol, the carboxylic acid, to the alcohol. So that's the idea, and that's what makes these important. And these are closely related to the molecules we see in metabolism in the body. Okay, as far as the oxidation of aldehydes, let me just see if I have some of this stuff here. Okay, yeah, that's just to remind me what to do. So what happens is that if we have an aldehyde, it's easy to oxidize it because this hydrogen can be cut off. Now, what happens is if you have a ketone, there's a reaction you can cut this R group off it, but it's not on the MCAT. You basically can't cut that. And it turns out that in organic chemistry, this occurs a number of times. Like, for instance, if you have an alcohol like this that has a hydrogen here, you can cut this. And when I'm talking about cutting, I'm talking about oxidation. This is what oxidation is. But if you have an alcohol like this, which would be, let's say, tertiary. So you put this alcohol here. Now what's going to happen is you're going to have the same thing. There's no way you could cut it. So what's the commonality? It turns out that this carbon is partially oxidized. And it's partially oxidized carbon is like a thread on a sweater where you can pull on it and it will fall apart. But if there isn't a thread, if that hydrogen isn't there, then you have a very hard time doing it, except by unusual reactions that are not in the MCAT. Another example, this benzene ring is also going to oxidize the benzyl carbon. So if you have a hydrogen like this, we'll put R groups over here, you can actually cut this. But if you have, similar to what we have above, like this, a lot of this stuff is pretty good to know because you can group ideas together in orgo. So this you can't oxidize. So the reason I'm talking about this here is that aldehydes are easy to oxidize, ketones are not. But then you can generalize this to other things. Now, what happens is that when you're going to go ahead and try to oxidize an aldehyde, let's take this. As far as naming goes, this portion here is called benzyl. So this would be called benzaldehyde. So I didn't mention the naming, but that's benzaldehyde. Now, if we take this and we react this with chromium in the 6th oxidation state, and we use H+, but no water, but no H2O. This is called Jones reagent. And Jones reagent could be H2Cr O4, chromic acid, as long as you don't have water. And it could also be called PCC. That's pyridinium chlorochromate. That looks really interesting. It's got a pyridine like this, and then it's going to have a hydrogen over here. This will be positive, and there'll be, it's really ugly looking, a chlorine here, and then CrO3. Okay, so anything that has chromium in the 6th oxidation state, like we have here, without water being present, will basically take this aldehyde and convert it into the carboxylic acid. So that will turn it into this right over there. Okay. And that's this reaction here. Let me just see if there's anything else I want to say about that. Let's see if this actually works. Okay. Okay, let's see. Well, that didn't work. Let's try it again. Copy. Paste. There we go. Okay, let's see. Previous. Yeah, there we go. Okay. I actually have said what I wanted to say with this. But it did lead me to a good place. Let me get back to this part right over here. Okay, good. I sometimes lecture and I leave things out because I get so excited, and I just made a list to see if I would get everything. So I did get everything I wanted to for that. There's another reaction called SWERN. You don't need the mechanism for sure, but you just need to know it does the same thing as Jones reagent does, as PCC does. And you take DMSO, and then this is called, I forget, but COCl2, I think methylene chloride, and then a base here. And essentially it does the same thing here. Is that right? Hang on. Oh, no, that's different. Okay, so what happens is I screwed it up. And so I'm now going to fix it. So what I'd like you to do is not to look at this. Okay, we're going to fix it. What happens is if you have a primary alcohol and you want to convert that into aldehyde, then the reagent you use to do that is PCC, that's Jones reagent, or it's going to be Swern. So what happens is it will take the aldehyde like this, the alcohol like this, and it will bump it up to this. And the thing about this is these are going to be really weak. And so this is going to be CR6 and H+, no water. And then Swern, which isn't used as frequently, is going to be DMSO. And then also, they have the other one in brackets. Oxalyl chloride, that's what it's called. Okay. So let me go put that in. You probably don't need that. I'm just trying to show off that I remembered it. Okay, that is oxalyl chloride, DMSO oxalyl chloride. And then in the next step, they add triethylamine. Okay, so those are ways of going from a primary alcohol and stopping at an aldehyde. And if you use any other reagent, it's not going to work just right for that. Okay, except for one. There's something called tolerance, but it's called tolerance test. Now I'm starting to do this out of the order I planned, but that's okay, which is why I screwed up. But there are chemical tests which are not intended to be done for reactive purposes, but are intended to be done for identification purposes. And this is done a lot with sugars, but essentially, if you have an aldehyde like this, and you react it with silver and a base, so there's a variety of bases you can use like this, but silver and a base, then what happens is that the sugar is going to turn into a carboxylic acid or carboxylate, and the silver is becoming a silver precipitate. So the reactions we saw over here, the reactions of PCC, Jones, and Swern, those are used to do synthesis. Tolerance is used to identify an aldehyde. Now, part of the MCAT is realizing that aldehydes and ketones, when part of sugars, are interchangeable. And that will explain the reactivity of tolerance test. And it will tell you what is a reducing sugar. A reducing sugar is something that reacts with tolerance test. So we're not going to actually go there now, but we will say that you will get a positive test, silver precipitate, when you use silver and base on an aldehyde. Okay, so we've gotten that taken care of with a little trouble. So now we're going to take a look at the cyanohydrin reaction. So with cyanohydrin, what you have is you have a carbonyl like this, and you're going to be using HCN or CN minus in quantity. And what will happen is you're going to get an OH here, and you're going to get a C triple bond N here. And it turns out that the way you do this is important because one will kill you and the other won't if you're not careful. So let's go ahead and have some fun. We'll turn this into this structure here. And then we'll use CN minus, and then here we'll have HCN. Now, the way this works is what's on top you have a lot of, and what's on the bottom you don't. And it's done by adjusting the pH. So essentially, you're going to have an equilibrium here. This stuff is hydrogen cyanide. They used it in the gas chamber to kill people in California. And so when you have very little of it, you're in good shape. It's dissolved. It's not a gas. So this is the way to go. What's going to happen is the cyanide will attack like this, and then these electrons will come up. So that is going to give you here O minus, and then the cyanide here is going to come in like that. And then finally, you're going to have the HCN like this. And what happens is this pair of electrons grabs this hydrogen, makes more HCN, and that's going to give you this. So this will give you the OH, and then this will give you the C triple bond N. And this is called a cyanohydrin. And cyano comes from the cyanide, hydrin comes from the hydroxide. That's the way to do it, unless you're like into Breaking Bad and you want to wear a gas mask and all. But the other way to do it, which works just as well synthetically, just more danger to you, is you come over here, and what you do is on top now, you put this. It's a gas, so you're under the hood and you're taking precautions. And then what happens is you've got the CN here. So when you do this, you adjusted the pH. So you got acid there. You grab that hydrogen there, and what you get is you get over here O, and then this is an H like this. So these looks like that. And then the cyanide comes in and it attacks, and this swings up. And there you go. So what you got is you got your OH and you got your CN. So the question is, why did they include this boring reaction that could kill you on the MCAT? And the answer is that cyanohydrin can be used synthetically to great purpose. And what happens is, if you take this and you react it with H3O plus, it will cleave this bond over here. And if you take this and you react this with a reducing agent like sodium, like a lithium aluminum hydride, you can do something equally interesting. I want to use lithium here. Okay, lithium aluminum hydride. Okay, so what this does, it's a hydrolysis of the nitrile, and it creates a carboxylic acid. So synthetically, it's pretty useful. And then over here, what happens is it puts on an OH, just like that. And then this becomes CH2, NH2. And this is the step one. Step two, you're going to add water. So let me make that look better. CH2, NH2, and then that's attached like this. So that's the real utility. It gives you the opportunity to create lots of different functional groups for the purposes of synthesis. Okay, so the thing is that we already did the oxidation of primary alcohols, but I got confused where I was. So now let's do the oxidation of aldehydes. Basically, this is very straightforward. If you have an aldehyde like this, and you use KMNO4, it's memorization, and hot, then what you end up getting is you get a carboxylic acid. That's how that works. And then if you come over here and you use K2CR2O7, H2SO4, and water, this is going to be CR6. But because of the water or anything aqueous, then it will go ahead and it will react and give you the carboxylic acid. So these are the two ways of doing this, of going directly from the aldehyde to the carboxylic acid. Now, if you reacted with either of these with the alcohol, they would also go to here. These are strong oxidizing agents. So I don't know if I can find it, but I'm going to try. Yeah, here it is. Okay. So I said, ignore that. So if you have a primary alcohol, you're going to get an aldehyde with any of these reagents. And once you form the aldehyde, it will go to the carboxylic acid if you use KMNO4 or K2CR2O7. So these guys essentially will take a primary alcohol, convert it into an aldehyde, and convert the aldehyde into the acid. And what happens with these, ran out of room, what happens with these is that you could start here and end up with the acid, or you could start here and it'll work the same way. Okay. So, okay. We've got the oxidation of aldehydes now, reaction of adjacent positions, enolate chemistry. Okay. So here's what happens if we have a molecule like this. This is the alpha hydrogen. And the alpha hydrogen is adjacent to the group of interest. And the group of interest, it's like an FBI thing, is the carbonyl group for aldehydes and ketones. For other groups, it's whatever is the group of interest. Doesn't have to be a carbonyl. So what happens is we take this and we react it with a base. We're going to grab this hydrogen like this. And when we grab this hydrogen like this will drop down and this will pop up like that. And what we're going to end up getting is we're going to end up getting C double bond CO minus. And this is called an enolate. And when you have a base, you always get an enolate. So what's going to happen is that this alpha hydrogen here is going to be acidic. And it's going to have a pKa, they vary somewhat, but for an aldehyde, it's going to be a pKa of about 17, which is not very acidic, but a ketone is going to be about 19 or 20, so it's more acidic than the ketone. Now, what's important about this is reversible. So just imagine if this was a chiral carbon here. So if this was a chiral carbon here, this is chiral. And this over here is achiral. And this is reversible. What that means is what was 100% optical activity, absolute configuration, will now be, in this case, racemic, because when it goes back and forth, it will racemize. And that's an important consideration when you have aldehydes and ketones. So if you have an aldehyde or ketone and the alpha hydrogen has a hydrogen on it and is chiral, under basic conditions, it will racemize. And I have news for you. Under acidic conditions, it will racemize as well. So that's what I'm going to show you now. So what we're going to do is we're going to come over here like this. We're going to draw the same thing. Oh, and by the way, I'm assuming that this is some kind of chiral configuration, which I didn't draw. And what happens is over here, we're going to add basically H plus to this. And what happens in a case like this, let's say H plus water, is this will come over here like this, and we'll get this here. Yeah. okay, and a positive like this. And then what's going to happen is the water is going to grab this hydrogen here, and these electrons are going to drop down, and these will pop up. Wow. Okay, so what we get is this. I didn't put my hydrogen on here. See where I put a, see where I put a hydrogen here. Let me get this out of the way. See, I put a hydrogen here, and then I didn't bother to put it there for some reason. So I just wanted to let you know, because you're yelling at me, okay, that's where it should be. And so then this will look like this. And then you have H3O+. So when it's acidic, you always get H3O+. You don't get negatives and stuff. And then this is called an enol. So in an acid environment, you get an enol. In a basic environment, you get an enolate. But it turns out that this is reversible also. So either an acid or a base, it's going to be reversible. And you're going from a chiral species to an achiral species and back. So under acidic conditions or basic conditions, the alpha position, if you can deprotonate it and if it was chiral, will racemize. Okay, so that is that. Okay, keto-enol tautomerism. Okay, so just to make it totally clear, that's enol, basic conditions, and this is enolate. I screwed it up. This is enolate, basic, and this, oh, I really screwed this up. Okay, wait, let's take a break. Take a deep breath. Here we go. Enolate, yes, basic, and this is enol acidic. Okay. Okay, that's good. Almost done. I'm basically going off their website here. I downloaded it and I put everything in so I could search what's there. Okay. Adol, okay, and then this, okay. Let's do the business with with kinetic and thermodynamic first, because it's more related to what we're doing. And then we'll do Aldol, and then we'll call it a day. So this over here is what we were talking about pretty much with alpha hydrogens. But what we didn't talk about was the fact that you could have two versions of alpha hydrogens on each side of the carbonyl. Now, what happens is that this hydrogen is hard to remove because of steric hindrance. And these hydrogens are easier to remove because of less steric hindrance. On the other hand, when we remove this hydrogen, the alkene formed, this enolate alkene over here. And by the way, this is basic minus H+. That's a little confusing that they did it that way. So here, this is more stable because it's a more substituted alkene or enolate. And then this is less stable. So when I say more stable, what I mean is 1, 2, 3, this is tri-substituted with carbons. And then this is di-substituted. So what happens is this. I changed the color on this, but in the first case, we're going way up to a very large transition state. And that's because of the steric factor here. But then, because this is tri-substituted, we're going to go down to a lower value over here. So what will happen is this is going to be more stable. So that represents the red. And then what will happen is with the blue, this will be easier. So it'll be a lower hill. But then this will be higher because it's less substituted. So this is going to be a lower hill like this, but this will be higher like this. And it's going to end up like this. So let me explain this now. There's two issues. One is the transition state, how hard is it to pull it off? And the other is the stability of the enolate, which translates into the product. And what will happen with this is there's going to be a temperature effect. This will be high temperature, and then this over here will be low temperature. So if the temperature is low, the molecule is going to be able to get over this hill, but not this hill. And so what you'll get is you'll get the kinetic product. So the kinetic one is the one that forms faster. So that's low temperature. Now, as far as higher temperature, if you raise the temperature up, this will equilibrate. The molecule will go into the red and the blue, and the one that has the lower energy, this is lower, so this will be lower, is the one that's going to predominate. So that's called the thermodynamic product. So the idea is the one with the lower transition state for a situation like this is going to form faster. And the one that's going to be more stable as a product is the one that will form at a higher temperature, because the molecule will go back and forth, and then it will accumulate at that higher temperature into the more stable form. So that's the idea behind thermodynamic and kinetic. Okay. And so the final topic for discussion is going to be aldol, which is an important reaction. Aldol reaction. Okay. So let's take a real simple case. What we'll do is we'll just draw a carbonyl like this, and then we'll draw another carbonyl like this, and then we'll just use OH minus. And what's going to happen is this hydrogen over here is going to be abstracted because it's going to be an alpha hydrogen. And these electrons go here and these go up like that. We've seen this. And then what we get is we get this over here, and then we get this over here like this. So this is going to be our enolate. Then what happens is these drop down to here, these come over here, and these pop over there. And that's going to give us this, an OH, O minus there. We'll have a bond here, and then a bond here, here, and like this. Okay, so the two electrons, the two carbons are here and here, just to make that clear. So it probably means I screwed it up because I should have two carbons there. Yes, I did. I'm going fast, but I will fix it. There we go. Okay. And by the way, this is alpha and this is beta. What happens next is we got water. And we're going to grab this here and over here. And then this gives us an OH. And then it gives us carbon, carbon, and then like this, double bond O. And what we have here is this is a beta hydroxycarbonyl. And a beta hydroxycarbonyl is an aldol product. Aldol product. Now, the reaction can stop here or it can go further. When a phenyl group is located on the beta or the alpha, it normally goes further. And when the temperature is elevated, it normally goes further. And when it does go further, it goes from an aldol to an aldol condensation. And the way that looks is essentially the OH minus, which is present, grabs this hydrogen, these drop down and this pop up. And then that's going to give us this. And then we have over here a double bond, and then over here and a double bond like that. And the thing about this is what we have here is this is alpha and this is beta. So this is an aldol condensation. And when it's aldol condensation, you're going to have conjugation, double, single, double, if you did it right. And the double will be on the alpha and the beta. So that's how alpha works. But if you think about it, this is alpha beta, alpha beta unsaturated. And then we're going to go from alpha beta backwards to beta hydroxy. This is how you do a retro-aldol. Retro-aldol is working backwards. So if we go ahead and we take this molecule, let me put this over here. If we go ahead and take this molecule here and we manipulate it, here's what we're going to get. We're going to go like this, like this, like this, and then we're going to turn this into an OH. So that's how we get the beta hydroxy. That's a simple way to do it. And then to get the final answer, what we do is we simply are going to cut this right here. And then the part that we cut it, the OH becomes the carbonyl. The OH becomes the carbonyl. So there's our carbonyl. And then over here, we've got our other carbonyl. So that's a simple way to work backwards. So alpha beta is the end, aldol condensation. Go back to the beta hydroxy and then cut and turn the OH into the carbonyl, and you're back where you started again. So that's called the retro-aldol. And I just want to show you something else. If you have a molecule that's a little bit larger, let's say you have this, I just added one carbon, then you would do it the same way. So I just added one carbon. This would be OH minus. And so this would be your alpha, and you would basically have this attack here. And so it would look like this, the OH would be here, and then this bond here would just be there. So that's, this here too. That's the difference, really. And then everything's the same. You just carry those bonds. So that's the way that works. And one last thing, since they brought this up, and I know that this is something that's asked a lot. When we're talking about an aldol condensation, if this hydrogen is not present, it won't happen because it's part of the mechanism. So what that means is if there's an R group here and there's no hydrogen, you may have lost one hydrogen, but you need to have two if you look at the mechanism to get the aldol condensation. So that's just something to consider. Well, thank you for sticking with me, if you in fact did, and I'll see you next time. Take care.